let's move on to our next speaker. So Qimiao Si is going to be talking about quantum critical metals, loss of quasiparticles, and the implications for flat bands.
Thank you, Doug. Let me share. You see my
Looks fine.
slides. All right, let me put in the presentation mode. Okay, should be good. Good, thank you. So, right. So I'm very happy to be part of this session. Thanks to everyone. Let me, so the title is already announced. Here's the plan. I want to just very quickly give a bit of the overview of the normal state part on the quantum critical metals and loss of quasiparticles coming, but the focus of the first part is to describe some work on the implications for superconductivity. Then I would like to, hopefully there's some time for me to talk about some implications of these overall lessons learned on studying the loss of quasiparticles for these geometric fat bands. So in many ways, the first part connects with what Silke Paschen talked about. The second part dovetails this d-electron connection that Megan had told us. Before I get started, let me acknowledge at least some of the collaborators, in particular, Lei Chen, a graduate student, and Hao Yu-Hu, who is now postdoc at Donnershire IPC. I just left in September, left Rice in September. I've had collaborations with Jed Pixley, Stefan Kirchner, former student and postdocs here, and long-standing collaborations with Kevin Ingerson's group from University of Florida, and the Silke Paschen's group from the Vienna University of Technology, and a bunch of wise people from whom I draw all sorts of inspirations. So the motivation of, excuse me, overall motivation is that we have a lot of families of unconventional superconductors, of which heavy fermion superconductors is a very venerable member. It's where the first unconventional superconductor was discovered. By now, it's grown to be a family of about 50 members. Many of them, perhaps most of them, we can make a statement about, have anti-ferromagnetic correlations of one kind or another. However, even in heavy fermion systems, quantum criticality and strange metal aspect is by certain metric still very modern in the modern have happened in the modern era, and the understandings of that have been made in this modern era. Our contention is that hasn't been adequately incorporated in the mechanism for superconductivity, and we wish to contribute to this problem, which in the process, it appears that there's some general implications for other unconventional superconductors as well. And to make the last point, here's a chart that is courtesy of Joe Thompson, which plots the superconducting transition temperature Tc against some T0, which can be interpreted as effective Fermi temperature. And the cerium-based and the uranium-based heavy fermion systems in this chart occupy this corner, and passing through some plutonium-based superconductors and connecting to the cuprates. And this line is a straight line, which tells us that Tc over this effective Fermi temperature is on the order of a few percent. So that would be my definition of high TC, in a sense that if you look at the BCS superconductors, this ratio would typically be 10 to minus 4 or 10 to minus 3 at most. So let me start by considering the normal state specifically on quantum critical metals. I think for the heavy fermion systems, at least some of them, there's no question that there's a quantum critical point that's anchoring the quantum fluctuations. In other unconventional superconductors, whether it's a point or a phase that's anchoring the normal state is still under debate. So let me just jump directly to the heavy fermion system with a Kondo lattice Hamiltonian, in which we have a species of F electrons which experience quantum magnetism with exchanging interactions between the moments. And then we have the itinerant electrons that are Kondo coupled with the local spins through antiferromagnet Kondo exchange interaction, spin coupled to particle hole triplet combinations of the itinerant electrons. That's the Kondo coupling. And motivated by some puzzles of in and last neutron scattering, as already alluded to, a number of theoretical studies were carried out. And the picture I wish to summarize it with is in terms of this antiferromagnetic to paramagnetic transition and a quantum critical point, which not only experiences fluctuations of the magnetic order parameter, but there's this destruction of the Kondo singlet, and this going from destructions to such extent that the Kondo singlet eventually goes away completely. Local moments talk to them among themselves, and the conduction electrons move in that background. And so this Kondo destruction is characterized by this E star scale that collapses to 0 at the magnetic quantum critical point. And so the destruction of the Kondo singlet creates or participates in the quantum fluctuations. So we've been doing that using this extended DMFT method. I'm not going to describe the specific except to say that it allows us to study the dynamical competition between the RKKY interactions, which wants to create quantum magnetism, and the Kondo coupling, which wants to create the composite fermions and heavy quasiparticles. And in this method, a key ingredient to look at the lattice model is to look at the fate of the local moment, including in the quantum critical regime. And that's described by a Bose-Fermi Kondo model with local moment coupled to a bosonic bath and a fermionic bath. The coupling to the fermionic bath is already the continuation of what's in the Hamiltonian Kondo coupling. The coupling to bosonic bath reflects the dynamical connection between the local moments through the RKKY interaction. So from what this is important as opposed to be, say, using the order parameter fluctuations, spin fluctuations, is to identify the possibility of additional fixed points. And so in this Kondo coupling versus this coupling to bosonic path parameter space, this would be the regime where Kondo effect has taken place and the composite fermions have been formed, large Fermi surface has been formed, and one would just do order parameter fluctuations associated with the spins of these quasiparticles. But by looking at asking the question of what's the fate of local moment in this amplified quantum critical regime, one has the possibility of an extra fixed point in which these Kondo singlets are actually destroyed. And this critical point is very interesting because one can, for instance, we can study the many-body spectrum to show that the many-body, this is the finite size spectrum calculated by a numerical opposition group method, to show that by the time you reach this red fixed point that's happening on this borderline, boundary, the quasiparticles are destroyed. And so this many-body spectrum is no longer described by the Fermi liquid quasiparticles. And that will be important for later considerations. You can solve the lattice problem in this overall kind of parameter space. And there are several different sequences of transitions which have been alluded to, but I will not go through it here, except that to say that I'm going to, for the rest of the talk, I'm going to focus exclusively on this trajectory in which there is a Kondo singlet formation that's responsible for the paramagnetic state. And there's the heavy quasiparticles, and the transition where the system goes to antiferromagnetic coincides with the destruction of this Kondo singlet. And so I want to just emphasize three consequences of that type of quantum critical point. One is that we were able to show that at the critical point, there's these dynamical scaling with the Planckian rate that comes into the scaling that's manifested in a scaling function. And that's the consequence that the spectrum is scale invariant at the finite temperature. KBT is the only energy scale in the problem. And this is very important because the work that started by Megan Aronson and the collaborators culminated in the work of Amo Schroeder, Gabe Apley, and collaborators on Sian Carpus Gold with this particular type of scaling with fractional exponent was the main motivation of studying this line of theoretical work. And we worked pretty hard to determine the exponent and found that it's compatible with the experimental observation. The consequence of that is that it leads to large Fermi surface associated with the composite Fermion formation to small Fermi surface jump across the second order quantum critical point. And that's been that's a point which has led to connection with a line of intriguing experiments, which I refer you to Silke Pashin's talk earlier in the session, including the Hall crossover and extrapolation to jump. And the third statement is that at the quantum critical point, the quasiparticle weights go to zero when it is approached from the paramagnetic side, and the quasiparticle weight goes to zero when it's approached from the other side. And so at the critical point, the quasiparticles are entirely lost on the Fermi surface. And that directly seeing loss of quasiparticle is very hard. And it was already mentioned that the recent short noise measurement showing that the Fano factor is reduced, and we'll hear from Doug Nathanson provides very direct evidence. I only want to mention that my student Yiming Wang looked at a problem which should have been looked at 30 years ago, but has never been looked at. Namely, if you have a diffusive metal with very strong correlations, quasiparticle weight could be, say, 10 to minus 3. But so long as the statement is, so long as the quasiparticles exist using this Boltzmann Langevin approach, we can make a statement that Fano factor must be square root of 3/4. So the experimental observation being small compared to that provides very direct evidence that quasiparticles are lost. So at this point, I want to talk about the implications for superconductivity. And we cannot do just EDMFT. We have to at least extend to multiple sites, in this case, 2 sites, because that's the only way to get unconventional superconducting pairing. And we verify that the quantum critical behavior captures what was already derived in the single site EDMFT. But there's a bonus here, which is that we can reveal along the way from Kondo to Kondo destroyed phase, there's some intersite singlet phase that exists in the phase diagram. This is purely just to impurity calculation. But this is important because the existence of such a phase means that fluctuations of it exist everywhere, including in the Kondo destruction quantum critical regime. And that's important because we believe that spin singlet correlations in a normal state should promote spin singlet pairing. And again, in this two impurity Fermion Kondo model, we found that to be the case. The irreducible pairing susceptibility is enhanced. It's only enhanced in a singular channel. It's suppressed in a spin triplet channel. And this enhancement is adequate to allow us to go through the calculation in a lattice problem to show that the spin singlet correlations in the normal state are promoted by the antiferromagnetic RKKY interactions in this environment where there's no static Kondo singlet in the ground state, but there's still dynamical Kondo correlation, so that what's happening in the spin singlet sector in a normal state in the spin sector can be transferred to the charge sector, including for pairing. And so we end up finding that TC over this effective Fermi energy is indeed on the order of a few percent. And we wish to use that to provide the understanding of, for example, serum rhodium indium 5 as an example in which there's a quantum critical point where Fermi surface jump has been established by quantum oscillation measurements that's accompanied by a tendency of divergence of the effective mass. So there's a very strong evidence. This is a quantum critical point in which all the quasiparticles are lost. And TC over effective Fermi energy in this material experimentally is on the order of a few percent. And this is what comes out of our calculation specifically for this regime. And we could generalize the calculation, which I don't have the time to talk about. But the statement is that this quantum fluctuations, very large quantum fluctuations of very large spectral weight associated with this loss of quasiparticles, or at least captured by loss of quasiparticles, can drive high TC decline in the sense. And in Sergei Pashin's talk, it was already alluded to that these kind of localization, delocalization phenomena already as captured by Kondo destruction quantum critical point appears to be happening in the cuprates, and at least in some of the cuprates, there's some evidence for quantum critical point. Not all the cuprates necessarily have quantum critical points. Issues still under debate, maybe quantum critical phase, but at least there's some phenomena that point to some linkage to this direction. And in ion-based superconductors, orbitals like MOT has been observed by Ming Yi's group from RPES measurements, and there's also some Hall measurement indications along this line for organic materials. So with that, I would like to make a switch to this F to D electron connection, specifically implications for geometrical flat bands. And point one is about fairly directly connected with what I just said, which is loss of quasiparticles. This question for us was actually motivated by the experiment at MIT and at Paul Scher's Institute about with indication of strange metal behavior in correlated Kagome metals. And so we, instead of studying Kagome metals, we decided to study a variant to it. It's the Clover lattice that Ming Yi talked about in her talk yesterday. And we're going to study one-band Hubbard model, just to make a contrast with what I'm going to be saying a bit more drastic. It's a one orbital model. And for simplicity, I'm going to use a 3D Z-square orbital for illustration. And so this Clover lattice shares the traits of a Kagome lattice in that there's destructive interference to the electron motion that leads to a flat band. We've actually did something to the lattice by breaking the C3 symmetry. We think it makes it makes it easier to study what we want to study, namely the flat band will be characterized by smaller symmetry, but still there's the mirror symmetry that's left. +1, -1, +1, these are eigenvalues of the mirror symmetry. So this is a dispersion, part of a dispersion without spin orbit coupling. This is a part of dispersion with spin orbit coupling. So you can see that the eigenvalue is changing from different points, special points of the Brillouin zone for this band. So it has to be topological. So topological obstruction kicks in, meaning that the topological nature of the band implies that we cannot construct the exponentially localized Wannier orbitals for this band alone. So in order to study local Coulomb correlation effect, we have to have Wannier real space description. So you have to combine the flat band with the wide bands to Wannierize it. So as a result, it becomes a multi-orbital model. So topology dictates that you cannot look at single orbitals. You have to consider multiple orbital models, but not in these Wannier orbitals. Not all the orbitals are the same. Some of these Wannier orbitals are very localized, and because they primarily comprise flat bands in K-space, and the others are have Wannier orbitals which are very delocalized. So there's hierarchy of the bandwidth associated with these wide bands, and wide band associated with the extended Wannier orbitals, and the flat bands associated with the localized, very localized Wannier orbitals. And the fact that these two bandwidths are very different opens up a new window of interactions, which leads to these orbital selective correlations. And in particular, it shows orbital selective Mach transition from large Fermi surface to small Fermi surface. And it's precise, the analogy with the Kondo destruction of the heavy fermion systems is very direct. So this is really where topology is setting up the problem to turn a d-electron system to be described essentially in a way which is a Kondo lattice. So these are Wannier centers forming a triangular lattice. This is multi-orbitals, and in this interaction regime, the mapping system can be mapped into a Kondo lattice description, and we can study the RKKY versus Kondo competition. The physics is an orbital selective Mach transition, but the description is very much a Kondo description. So, Doug, do I still have like 2 minutes? Where am I in terms?
Yes, yeah, you still have a couple minutes.
Okay, thank you. So with that, so we haven't studied the strange metal physics or even dynamics that much, but this just raises the possibility that through this topology-enabled setup of molecular orbitals, we can have the quasiparticles which are formed essentially by this Kondo physics, and then destroyed by the competition through this orbital selective Mach description. And so the loss of quasiparticles connect such systems to the heavy fermion materials, and perhaps the strange metal behavior that's observed in these materials is natural. And I should emphasize that experimentalists have already made these kind of intuitive connections, but the topology made the setup to be precise. Now, so I want to turn to, in fact, topology. What I've described for you is a bit simplified. We want to set up a problem, so we put the flat band to be at the Fermi energy to begin with. But genetically, these geometrical flat bands are located far away from the Fermi energy. And so we take a model in which the geometrical flat band is very far away from Fermi energy. And in this most recent piece of work, championed by Lei Chen, we found two things. One is that correlation can produce emerging flat bands which are pinned to the Fermi energy, in addition to some incoherent satellite-like features. And the second, because the flat band, geometrical flat bands are very naturally topological, these emerging flat bands host correlated topology in the form of topological Kondo semimetals. If I use the language of Kondo that I described just now for this d-electron setting. And so let me just very quickly expand how this is the schematics is derived. One is that instead of going through the strange metal, loss of quasi-particle physics, I'm going to stay on the delocalized side, but there's a very strong orbital selectivity. The Z of some of these 1-year orbitals is the quasi-particle weight of some of these 1-year orbitals is much smaller than the others. So this is the orbital selective regime, the metallic side, but it's influenced by the physics of orbital selective phase. So that's the interaction that's relevant to this illustration. To show that, this is a non-interacting dense of states showing the flat band schematically illustrated here. And this is the interacting dense of states showing the emergent flat band with satellite features and some background electrons. And this is the dispersion of these emerging flat bands. And they are very narrow, confined to the vicinity of Fermi energy. And if you zoom in, you can see that the symmetry protected nodal excitations that captures the topology. And we studied a very simplified model, but if you go through more realistic models, you would expect something like Weyl Kondo Semimetals to be associated with this emerging flat band. And we believe, and we want to put forward this analysis as advancing a design route for topological Kondo semimetals, specifically Weyl Kondo semimetals, but in these d-electron-based materials. So for the f-electron-based materials, we had recently a design route of this kind, which says, how do we start from a database of materials with some specific space groups, using the criteria of them being semi-metals, and using the criteria of them being correlated as forming this flow chart. And if these are square nets, very popular symmetry that was also discussed yesterday. And in fact, we identified 2 materials in this inversion symmetric case, and 1 material in this inversion non-inversion non-central symmetric case. And experiments actually have provided evidence that this flow chart actually has validity. So here we want to add for d-electron materials using the same flow chart, but add the requirement that the lattice would host flat bands based on symmetry and other considerations. And so this is a design principle that's to be tested. So let me just quickly summarize. I talk about quantum criticality from Kondo destruction, the loss of quasiparticles, and how that promotes unconventional superconductivity with TC that's high compared to the Fermi energy, and talked about these implications for flat bands. Thank you.
Thanks, Qimiao. We have time for a question or two. I'll perhaps just ask a naive one. So there's, when one measures and talks about a diverging mass at one of these transitions, it seems to me it is the diverging mass of a quasiparticle that at the same time is happening with the disappearance of quasiparticles. Now, in a sense, I understand that, but is there something more subtle about that situation?
Yeah, that's a good, sorry, I destroyed the slides. I hope I'm sharing. Yeah, so good. So so the point is that there may be, it's a very general question, and I'm not sure there's a unique answer. But there are 2 cases where I can give some insights. One is that the case that I considered has the quasi-particle, it's a second order phase transition. So the quasi-particle is going away and something else happening. There must be continuity dictates that the quasi-particle weight has to go to 0. And the quasi-particle weight going to 0 makes the system to be very sluggish and what remains of these quasiparticles, it would have to be very heavy. So there's no contradiction in the sense that this is a statement that only applies over a temperature window that becomes progressively smaller. That's one way of thinking about it. The other is perhaps just not even resorting microscopics. Already, for instance, the Brinkman-Rice picture of the Mott transition, if you are narrowing the band, that's also interaction-driven narrowing of the band, and quasiparticles becoming more and more progressively fragile, and the quasiparticle motion, the velocity becomes smaller and smaller. So I think in principle, it's allowed scenario, whether it's a general statement or not. That's a very interesting question.
All right, thanks. Let's try and keep on time. So maybe Yonglong, if you could put your question in the chat.
Yeah. Okay.
Thanks again, Qimiao.